I think the real bottom line with this is I shouldn't have assigned those three problems yet. But so that's the first thing I'm going to talk about. Oh, I got to plug in. Uh, that's the first three things I'm going to talk about right now, and then I'll go back and get a couple of those problems. Um, so to find a force with a known direction and an unknown magnitude. This is something we're going to do all the time this semester. And the basic idea is that, if you have your coordinate system and we want to represent a vector that has a magnitude r, and we don't know what that r is, but we do know the direction is, let's say 40 degrees like that. Well, the components of the vector are always going to be the length of the vector times the cosine of that angle theta, L times the sine of that angle theta, where theta is the counterclockwise angle from the positive x-axis. And so in this case, we can call this r cosine of what's the counterclockwise angle from the positive x-axis to that vector? 140. Yeah, 140. And so then if you just plug that into a calculator, you get like negative 0.766 R, 0.643 R. So this is how to approach it if it's a two-dimensional problem. Where you're given angles. If instead of angles, you're given reference points, this will come up sometimes in 2D. But this is always how you're going to approach it in 3D. So let's say we have a case where there's a wall over here, and connected to the wall is a cable, and then that cable is connected to an object, and we don't know what else is going on with this object. There's other forces acting on it, maybe, or whatever. But let's say that we're not given what the angle of that cable is. We're just told that in our coordinate system, the coordinates of this point are 14.5 for x, negative 7.0 for y. And the connection point here is positive 16.5 meters for x, negative 8.0 for y. And the question is, if the cable tension is some unknown value t, what's the force vector the cable applies to the object? Okay. So in this case, there's no way to do this by, determining that angle theta. The way you have to do it instead is, so we know the direction of this force vector is going to be this way, away from the object along the cable.
It'd be in the second quadrant, so
right?
X will be negative and Y will be positive.
That's right. So what we want to do, notice that when we use cosine and sine, what we're really coming up with is a unit vector. The cosine of 140 and the sine of 140 gives us a unit vector. So we're just going to use another approach for finding the unit vector here. And the way we're going to do it is we're going to take 14.5, negative 7.0, minus 16.5, negative 8.0. And that gives negative 2, positive 1. And that is a vector pointing to the wall connection from the object connection.
I have a question.
Yeah.
How do you know that was that direction?
Oh, yeah. Okay, so cables always apply forces to objects parallel to the cable and away from the object that you're isolating. So the object that we're focusing on is that box thing, and so it's going to be parallel to the cable away from the box thing.
Professor?
Yeah.
So like you say, so it's from the object to the stationary thing?
Yeah, just in this case, I mean, if we were trying to calculate the force that cable applied to the wall, then everything would be in reverse.
Okay. So if we have two objects, is it specifically going to ask us, is it from like the box to the wall box?
Yeah, it might not word it like that, but you always do have to make that, you have to get that from the context of the question. Okay, so first we have this vector that's pointing in the right direction, but it's not a unit vector yet. So I'm going to call this our vector just u.
So it's still not a force vector because it's not a unit vector.
Right, so the force vector has to be the magnitude of the force, which will often be a variable because we don't know, times a unit vector in the direction. And so we're finding a regular vector in the direction, then we're going to normalize it to get a unit vector, and then we're going to multiply it by t. Yeah. And so now we'll say to get the unit vector, this is going to be, 1 over the square root of the sum of the squares times that vector. So that's negative 2 times This is 4 plus 1, so square root of 5. So negative 2 over the square root of 5. Positive 1 over the square root of 5. So that's the unit vector in our direction. I usually just put everything in decimals, so 0.894, 0.447. And now that we have a unit vector representing the direction, the force vector is just the magnitude of the force times the unit vector. And so that's negative 0.894 t, positive 0.447 t. So this is going to be a really useful thing that we're going to want to think about, separating the direction from the magnitude. So separating the direction from the magnitude will be very useful to us.
I was playing around on my calculator and it seems like there should be a way to give it a vector and it outputs into unit vector.
Yeah, what calculator do you have? Yes, yes. On the TI 89 and the Inspire, there's a function called, what is it called? Norm? I think, oh no, okay, the one you want is unit V. And you input the vector, so like in this case, it would be negative 2, 1.
Okay, the easiest way to do it, you can type it in, there's a button, you'll bring in your brackets, you'll separate each year numbers, comma. That's
Yeah.
the easiest way to do it.
Yeah, they're all different, but all of the TI calculators do it differently, but yeah. Yeah, so I guess in the Inspire, you would enter it like, yeah, I'm going to just leave it like that, I guess. In the Inspire, you would put it in like this, and it'll spit out a vector negative 0.894, 0.447. If you have an 84, 83, 86, it's pretty easy to write a program that does this. So let me know if you want my help getting that program entered. Just saves a few keystrokes. You know, we'll use unit vectors all the time. Okay, so let's go through a couple of those problems you asked about from the homework. So let's do 14 to start with. So we're going to assume the cable tension is T. And it gives us the 2 points. Okay, so what's a vector that starts at the point A and goes to the point B? You would always do that as the coordinates of B minus the coordinates of A. And so B is 4, 2. A is 1, 1. And so a vector that goes from A to B is 3, 1. So that is a vector like this. The force vector, the cable applies to the beam. Okay, so this is like the example we just did. We need a unit vector in that direction, and then we need to multiply it by the magnitude of the force, which in this problem is T. So a unit vector, the little caret hat thing, means a unit vector in the direction of u. So this is 1 over 3 squared plus 1 squared square root times 3, 1. So that is 3 3 over the square root of 10. So 0.949. And then 0.316. So that is a unit vector in the direction from A to B. And then the force that that cable would be applying to the point A is 0.949 T, 0.316 T. Then it's sort of asked to do all the stuff in the reverse direction. So what's a vector? What's the vector that goes to A from B? Now, we just subtract in the opposite direction. So this is going to be A minus B. It's always the destination, the final point, minus the starting point. So this is 1, 1. And it's probably pretty clear to you that we're just going to get the opposite answer we got before. So 1, 1 minus 4, 2. And so this time we get -3, -1. When you take, and now we want to calculate the force that that cable applies to the wall. Okay, so this time our object of interest is the wall. And so the force vector that we want is, the head and the tail are switched of the one that I have drawn here. So our unit vector this time is -0.949, -0.316. And so the force vector is -0.949 T, -0.316 T. Yes?
Can we just leave it like without the decimal? Can we just do like -3 over root 10 T? Or
Yeah, let's see. Is that we're going to do numerical solutions to things. So, I mean, that's fine as an answer, but I think a lot of times you're just going to have to turn it into a decimal to put it in your calculator to solve stuff.
Okay.
But yeah, you're welcome to
My
leave.
calculator, it does the fractions sometimes, so
Yeah. Okay.
I like it.
If you ever if you ever have an exact solution like that and you want a decimal, I think all of
you
you,
just press control and then equals and it gives you-
yes, it'll do that. And right. So if your calculator says 3 over square root of 10, and you want to know what the decimal answer is, just hit, in mine, it's the white button and then enter again. And it'll give you the decimal solution. So sometimes in this class, you're just going to need to know the decimal solution because you're going to enter it into something else. Also, if you go to mode and scroll down, if you want to, if you change the exact approximate thing to approximate, then it'll always give your answers in decimals. You don't need to do that, but it's nice to know how to do that. Sometimes it'll be useful. Okay, so that's number 14. And then number 15 is just doing the same thing, but in 3D instead of 2D. I'm going to skip that.
So, question, are 14, 15, and 16 still due today?
If you want to turn those in with the assignment for today, that's fine with me. Yeah. So our assignment that I give you today will be due on Wednesday night, by Wednesday night, since there's no school on Monday. Yes.
You go over part B of number 16.
Sure. Yeah. Let's see how I get there. Okay, there's 16. So we are given coordinates for a bunch of these points. So where the cable attaches to the body, the coordinates here are 0.6, 0.4. We're given that this angle is 45 degrees. And the pin down here is at the point 0.05, negative 0.2. Okay. And the first question is, if the cable has tension T, what's the force vector that the cable applies to the body? Okay, so the force vector that we want is this. We want a unit vector in that direction, and then we want to multiply it by t. Okay? Everyone with me on that? We're given that that angle is 45 degrees. So we can, to calculate that unit vector, we can just use cosine and sine. So here's our x-axis, our y-axis. Our theta is this, just 45 degrees.
That's just root 2 over 2 root 2 over 2.
Right. Yep. And so we're just going to go, the magnitude of this thing is t. And so that force vector is t times the cosine of 45, t times the sine of 45. And as a decimal, that comes out to be like 0.7071 t, 0.7071 t. And so that's the force vector. And then the next one is, let me get rid of that stuff. We want to calculate the vector from the pin to the point where the cable contacts the wall. Okay. We don't have, like, if we had the coordinates of the point where the cable contacted the wall, we could just do the subtraction. But we don't yet. So what we want is, we have the coordinates here. If we figure out the vector that goes from here to here, so if we can express that vector, remember that coordinates, like the definition of coordinates, is just a vector from the origin to that point. So we can just think of coordinates in terms of like vector additions. We have a vector from the origin to, like, if we want to come up with the coordinates of this point here, and we have the coordinates of this point, the 0.6, 0.4, are a vector going from the origin to here, then a vector going from the origin to the point we want is just the sum of these two vectors. So what we're going to do is just start with the coordinates that we know and add the vector that we're going to figure out, that black vector, and that'll give us the coordinates of this point. What?
For A?
For the point, we're on B now, and we're trying to figure out the coordinates here.
So for A, we didn't need to add the 0.6 and 0.4?
No, we did not, because we just had the direction. All we were trying to do was come up with a unit vector in the right direction and multiply by t. Okay, so for part B, I'm going to call this vector u. We know that the magnitude of that vector, the length of that vector, is 0.5. Like, now we're not talking about forces anymore right now. We're just talking about the length, an actual physical length, like in meters. So this is going to be 0.5. This is the one that I'm calling u. So this is 0.5 times the cosine of 45, 0.5 times the sine of 45. And that gives you like 0.3535, 0.3535. And now we can say the coordinates that we want are the coordinates at the tail of that vector, 0.6, 0.4, plus 0.3535, 0.3535, and so you get 0.9535, 0.7535.
Do they do these vector that we, no. Do they do vector that we?
Yeah.
Like the 0.5 7.5, that's like the magnitude?
We're told that that cable has a length of 0.5. So the magnitude of that black vector that's drawn here is 0.5. And then we're multiplying that by the direction, and we know that this angle is 45 degrees.
So the coordinate that we get is like at the top of the arrow?
So this vector, the 0.3535, 0.3535, is the components of this black arrow. And then we add that to the coordinates at the tail, and it gives us the coordinates at the head.
Yeah.
Sure. Any other questions about that one? This stuff, as we go on in this class, is going to become pretty, familiar. We'll do a lot of that kind of stuff. So just little by little, it'll start by making a little sense, and little by little, it just be sort of what you do naturally. Yeah.
How many things?
Oh, yeah. Yeah, that's an important question. I don't care at all about sig figs, I guess. So you can just round off as you see fit, basically. Yes.
In question B, it's supposed to be the pin to the point where the like another sort of like direction, right?
The vector from the pin. Oh, yeah. Okay, right. I didn't finish that problem. Thank you. So the coordinates we want are these, right? That's the coordinates here. But now we want a vector that goes from the pin to the location we just found the coordinates for. And so that now we can just subtract. So we're going to go 0.9535, 0.7535 minus the coordinates at the pin, 0.05, negative 0.2. And so we get 0.9035, 0.9535. The units are meters. And I'll show you that vector up here. That is the vector from here to here.
When we're doing problems like this, is there any way we can just differentiate between coordinates and vectors because they both have the same bracket? So just same bracket becomes either vector.
Think of them all as vectors. Think of coordinates as a vector from the coordinate system origin to the point, and vectors is from vectors are like you're used to vectors being. So really coordinates are vectors. Okay. Any other questions on that one? Okay, one thing that is also going to come up a bunch and is going to come up in the next set of problems I assign is, I don't have a better way to describe this, so I'm going to call it piggybacked angle references. And so I have an example here that I think will sort of point out what I'm trying to do. So let's say that we have a problem where we have a floor, and then we have a wall, and let's say that the angle between these are 25 degrees, and then we have a slot like this, and we're given that the angle between the wall and this slot is another, what does that look like? Let's call it 60 degrees. And let's say that we want to find a unit vector perpendicular to the slot. Okay, so it's easy to look at a question like this and just your brain sort of short circuits. There's just sort of too much going on. But there's a very systematic way that you can think about stuff like this. And this is going to be something that we're going to want to get used to as this semester goes on. So what I'm going to do is I'm going to draw out my coordinate system. And I'm going to start drawing vectors that are in directions. So when I say piggybacked angle references, what I mean is you look at this problem and there's like, okay, you can see that the wall angle is referenced from the floor. And then the slot is referenced from the wall. And then 90 degrees perpendicular to the slot is referenced from the slot. So that's what I mean by their piggy bank. They're not all measured compared to, say, the floor. Okay. And so what I'm going to do is, one by one, I'm going to go through and define vectors that help me break this up into steps. Okay. So I'm going to first define a vector like this that's 25 degrees from the floor. Next, okay, you don't have to do it this way. This is the way I'm going to do it. I'm going to take the vector in the opposite direction. Okay, so that is 180 degrees from this. Now you can see the slot is 60 degrees from this vector I just drew. So this angle is 60 degrees. And then finally, I'm going to go 90 degrees from that. And I could go either up or down. There are two perpendicular directions, but I'm going to choose the one this way. And that is 90 degrees from this. It looks cluttered with all these angles drawn in. But so now what I'm going to do is just add up those angles that I've figured out. So my theta is going to be from the positive x-axis I went 25 degrees counterclockwise to get here, right? So counterclockwise is positive, clockwise is negative. So I'm going to go, first positive 25 degrees. Next, from this one, I went counterclockwise 180 degrees. That's positive. So add 180. Now that we're here, I went 60 degrees clockwise. Clockwise is negative, so now I'm going to subtract 60. And then my last step from here was I went 90 degrees clockwise. So subtract 90. And what do we get? 90, 30, what? 55?
Yeah.
So this is positive 55 degrees. And so a unit vector that's perpendicular to that slot is just cosine of 55, sine of 55. Okay. And that is 0.574 0.819. Any questions about that? Okay, well, seems like a natural place to stop. The next thing we're going to do is really the first statics. Now we're done with talking about vectors and stuff. I'll assign the rest of the problems. They'll be due on Wednesday. And then we'll start talking about particle statics next week. Okay, have a good long weekend.